All right. Hello, everybody. Good morning, good afternoon, depending on where you are in the world. But I want to welcome you here to this webinar and thank you all for attending. My name is Jeff Rossio. I'm the manager of digital marketing with Harvey Performance Company. I'm going to be moderating the webinar today. And so before we get started, really quick, just a couple of things. Um, we we cannot hear you, but you can hear us. So the way to communicate with us during this webinar is going to be through the chat. The live chat is on the right side of your screen on desktop and on the bottom of your screen on mobile. That's going to be the best way to get in touch with us. I will be in the chat under the Harvey Tool username, and we also have two application engineers who are going to participate in the chat and can help answer questions along the way. We have Reese Trotter and Adrian Hart. So if you see their names, they are with our company. They can help you out with any of your questions. Then we have Don Grandt, National Application Engineer, who's going to be presenting here in just a minute. And this presentation is going to be about 45, 50 minutes, and we'll have a few minutes at the end for some last minute questions and conversation. So with that being said, I am going to pass it over to Don now and let him run with it.
Hey, thanks, Jeff. Appreciate it. Well, as Jeff said, my name is Don Grandt. I'm the National Application Engineer for the Harvey Performance Company. Thank you to everybody joining us today. Appreciate it. Just to give you a little background on myself, I've been in the cutting tool industry for over 32 years, actually making cutting tools, using cutting tools, breaking cutting tools, fixing cutting tools, and all of the above. So hopefully my experience, you can benefit a little bit better from this presentation, and we're going to walk through it. So first thing I'd like to kind of start off with is just tell you a little bit about Harvey Performance real quickly. We're sponsoring this webinar. We're actually doing a series of these, but Harvey Performance Company is kind of the umbrella company for three companies that we're actually involved with. Is Harvey Tool is basically our miniature and specialty cutting tools. Helical Solutions is also a brand we have, which is your high performance material specific end mills, more your larger diameter tools. And then Micro 100 is your micro turning, miniature specialty turning tools. So you can see from all three of these brands, we have a lot of experience in cutting tools. We have a lot of experience on how to apply those tools. And with all three brands, we also have a lot of experience solving a lot of problems at the spindle. All solid rounds, and that's kind of what we're going to talk about today. So let's just go over an overview of what we're going to talk about, and let me get a little bit descriptive on each one of these bullet points here real quick, so you can understand what kind of content we're going to be going over and how you might be able to benefit from it. So the first thing we're going to talk about is end mill anatomy and cutting geometry. We're going to do this a little bit different when we run through this. So we're going to talk about simple anatomy on an end mill, but what I'm going to do as a twist is I'm going to throw in some of the hints, tricks, and benefits of that geometry and what you're kind of looking for on an end mill and how that affects what you might be cutting. So that's what we're going to start out with. Then we're going to jump into end mill wear patterns, which will kind of go with the end mill geometry. We'll take a look at some of the common wear patterns that you're actually going to see on your end mills, some of the remedies we can actually take in fixing those wear patterns, and how to identify those and what some of the problems might be. Then we're going to jump into drill point geometry. Harvey Performance, Harvey Tool sells miniature drills up to 1/4 inch. So we're going to talk about drill point geometry. And like I said, I have 32 years in the industry. I'm a little bit partial to drills and drill point geometry. It's kind of where I started in the industry. So one of the most important parts of a drill is the point. So we're going to talk about how that is going to benefit what you're actually doing and making holes and concentricity and the rest of it. Then we'll jump into some coolant benefits, kind of a good, better, best scenario and how that benefits drill point geometry and drill pointing and end milling. And then at the end, we'll finish out with tool holding and run out, which has to do with a lot of the issues you're going to encounter with all of these. So let's jump into end mill anatomy first of all. So the first thing, which is the most common, is a cutter diameter on an end mill, right? Every end mill has a diameter that you're actually speccing to your machine with that tool. The measurement is basically taken on the outside of the tool. We call it the margin, even though it's up sharp on end mills. Some aluminum tools do have a margin on them, but it's taken usually on the last 10% of the diameter of the tool. Now, this measurement is actually what you're going to put in your software to control the dimensions that you put on your material that you're actually cutting. So I wanted to kind of bring this up with the cutter diameter to let you know that usually industry standard tolerances on an end mill, a 1/4 inch and up, is a -0.02 on the cutter diameter. So just be mindful of that when you're actually getting a 1/2 inch tool, that you either one can mic the end of your tool or you can laser mic it, check that diameter and make sure you're inputting that information into your software to make sure that you don't cut it undersize. Either that or the fact that I am an old school machinist, you can tell it that you have an oversized cutter, in which case you'll stay away from your wall and you won't cut undersize. But critical cutter diameter is the number one. That's the OD of the tool running all the way through the shank. Shank diameters on a tool are usually H6 tolerance, which is a -1/10, -4/10. And that's usually built in. If you see the word H6 tolerance on anybody's diameter for shank, it usually is good for shrink fit. So H6 is your shrink fit tolerance. Then let's jump into helix angles. Helix angles are a very important part of an end mill. It's basically the angle of the flutes off the center line of the tool. So why is a helix angle important? We probably all looked at cutting tools and we see maybe some have a little bit slower or a lower helix. Some have a higher helix. What is the helix I'm looking for on my tool? Well, let me explain what a helix angle actually does in an end mill. Usually, and not usually, this is fact, the higher the helix angle, the more downforce that you're going to have on the end mill, which means the more it's going to want to corkscrew and pull out of the holder. The benefit of a higher helix is actually going to give you less radial force. Now, the radial force is what is pushing up against your material. So I bring this up by saying, if you're doing finishing applications, you're using the whole length of cut on an end mill, and you're getting taper in your wall or you're getting deflection, one thing you can look at is look at your end mills and try and find something with a higher helix on it. What that will do is that will put less force on your wall and it'll cut a lot freer. Okay, flute count is going to matter too as well. Now, if you go with a lower helix or a slower spiral, one that's going to lay down more, what that's going to do is that's going to give you a stronger end mill. It's going to give you a stronger tool, a little bit more for roughing, but it's going to put a lot more radial force, but a lot less corkscrew force. So you're not going to be as apt to pull out of the holder. So if you are having pull out issues, and that's one of the main things, and you can't change your holder and you just can't stop that, one thing you might be able to do with the end mill is take a look at that helix angle. You might be able to just combat that down pulling and that pulling out of the holder by going with a slower helix. Now, it's going to put more radial force, but it depends on the application and it depends on what you're actually doing with that end mill. So think about that. Faster spiral, faster, it's going to put less radial force on, but it's going to pull out of your holder a little bit more. It's going to put down force. Slower spiral, lower helix is actually going to put more radial force, so you're going to get pressure against your wall, but it's going to be stronger and it's not going to pull out of your holder as much. So it's very important to take a look at the helix angle for what you're doing. Consult the experts if you need to, but it's a little bit better understanding on how that helix angle affects how you're actually cutting. Another tip with helix angle is, if there's any older school machinists that are on the line, there's something called back in the day, and even it's relevant now, but there's some things to combat it. Back in the day, tool pressure is a big issue. So the more flutes you have in contact with your material, the more tool pressure you have, right? So now we can combat that a little bit with helix angle too as well. A slower spiral is going to put less flutes in contact with your material, and it's going to put less tool pressure. Now, I said it was a little bit old school because some of that is combated a little bit with new technology and core strength and flute count. So core strength kind of combats a little bit of tool pressure, whereas helix angle used to do it a little bit back in the day. Hopefully that wasn't too confusing, but we can get into that a little bit more at a later date. So the flutes, what's the flutes? The most common part of an end mill. The flutes are basically what's going to hold your chip. That's what's going to create your helix angle. That's what's going to create your rake face. And that's what's going to hold your chip to evacuate your chip. So you can see these slides together. We have flutes on the top, and then we have flute number on the bottom. So your flute count is exactly how big of a chip we can actually hold for that chip to evacuate. So you can see on the left-hand side, we have 2 flutes, which is going to give you your optimal chip space and the most room that you can carry the chip. So you're going to use a 2-flute end mill for your softer material, where your radial step over is going to be real aggressive, and you're just going to hog that material off. In aluminum, you're going to look at your 2 and 3 flute end mills because it's softer, and we're going to be taking 30–40% radial step over, and you want the biggest chip room that you can possibly put in there. If you're running 1018 in your ferrous materials, I wouldn't even suggest a 7 flute or an 8 flute or a 10 flute for 1018 material, even though it's ferrous. I would start looking at your 4 flutes because you're still going to take a big radial step over. As your material starts getting harder and you need less chip room because we're going to take less of a radial step over, now we can start getting the 5, 6, 7 flutes. We're going to have less chip room with those flutes, and we can evacuate the chip accordingly. So variable pitch. So this is a slide that I have for variable pitch, but there's actually 3 versions of what we're trying to do with variable pitch. Variable pitch on an end mill is basically taking the symmetrical form of the flutes, say 4 flutes, and indexing those 90 degrees on an even spacing and offsetting the pitch on that. So it's not equally 90 degrees. Now, why would we do that? Well, when you're running end mills and you're running in materials and mainly in your super alloys and your heat resistant end mills, when you start getting at an elevated RPM, you want to get the end mills want to get a natural harmonic, a vibration. And they want to start kind of humming along, almost like driving a truck down the road with big knobby tires that starts humming. When you get that humming on there, you want to kind of break that up somehow. So there's really 3 ways to break up the harmonics on a cutting edge on an end mill. You can do variable pitch, which is the picture I actually have here, which offsets each one of those teeth, each one of those flutes, so it's not symmetrical in 90 degrees. You can do variable helix, which if we go back a slide or 2 slides here, where that helix, instead of being 38 degrees for all 4 helix, it will actually be 38 degrees on one helix, 35 degrees on another, maybe 32, and then back with a 37. And that'll give you variable helix to offset that flute and that vibration. And you can go with a progressive helix, where the helix starts out at 1 degree and then changes as it rapids up the spiral. So maybe it starts out at 32 degrees and it finishes at 38 degrees. So there's really 3 ways to break up those harmonics. Helical Solutions actually runs with a variable pitch. We've done testing. Larger diameter works very well to run a variable pitch. Harvey tool on the smaller tools runs a variable helix. So the helix varies on that. Works a little bit better on smaller diameters. Some people will do, or some vendors, some cutting tool companies will do a combination of both. Benefits in that. and some will just kind of change each one of those formats. But what you're trying to do is you're trying to break up those natural harmonics, which is going to give you a bad finish, which is going to give you poor tool life, which is going to give you chipping. So axial relief, if you look at an end mill and you look down at the end mill, the end of the end mill has to cut. In most cases, it has to cut. Either if you're ramping or if you're plunging, you need axial relief on the end of that tool. Basically, there's a primary and a secondary in there. The axial relief on the end of the tool causes the tool not to rub. It gives it clearance. It gives you a primary and a secondary. So when you're ramping on the end of the tool, you're cutting on the corner, but you're actually giving the tool relief so the chips can evacuate and it doesn't rub and cuts free. Now, if you have one tooth, if you look at this 5 flute, you can see you have one tooth to center. You want to look at your end mills, and most end mills solid carbide today in this market, I'm going to say most, I'm going to say almost all of them, actually are center cutting up to a certain diameter. You want to make sure if you're going to plunge with that end mill, which means you're going to take that end mill and you're going to plunge straight down. Now, is plunging with an end mill recommended? No, I would rather see a helical ramp where you're actually spiraling down to actually make your cut to get to the bottom of a hole or to get to the bottom of a surface. But will an end mill plunge? Absolutely, 100% an end mill will plunge. I would recommend if you're plunging to use like a G83 PEX cycle or something like that with an end mill, because the chip evacuation on plunging an end mill is not very efficient. And it's not going to work as well as if you're using a drill or another method to get to the bottom of that hole. But at the end of the tool needs clearance on it in order to do that. Core diameter. So core diameter is very important to an end mill. Core diameter is what's going to reduce your deflection. Your deflection is what's going to cause all kinds of problems. So when we have a smaller core, we get maximum chip space. Smaller core is going to give us maximum chip space. It's going to give us smaller number of flutes. It's going to decrease the tool strength. So what we want is we want to try and get in any application, we want to get the largest core as possible, especially when we're doing high efficiency machining where you're taking a long axial depth of cut and you're taking a light radial depth of cut. This is HEM. We're going to do a whole training on this. So I suggest you join us. The HEM presentation we're doing is going to be great. But when you're running these HEM techniques, you really want to start looking at the core of your cutting tool because you don't need the chip evacuation. And that core is what's going to help your rigidity of that tool. Some people will do oversized cores. Some will do a standard core. You can find different variations of this. It's good to consult your vendor for end mills to find out what core is recommended for your tool path. But core strength is key, and core strength is basically what's left over after the flutes are created on your end mill. Or drill too as well. On a drill, it's called a web. We have this, I have this standing, not argument with some people because I'm a drill guy, but it's a web on a drill, it's a core on an end mill. So just to differentiate those two. So the end gash is pretty obvious. Really, the end gash on the end of the tool is there to support the end cutting geometry. It's giving you your chip space. It's creating your clearance. You have to be very precise in grinding all these features together. At Helical Solutions, there is a huge science that has gone into creating this geometry because you don't want to overcut the gashing. So you make it weaker so it doesn't perform. But then again, you don't want to undercut it because then you're not going to have enough chip space and you're going to have the opposite effect when you're using that feature. So the end gash is what's actually creating your clearance for the chips when you're plunging, when you're ramping to get them out of the end of the tool and to create your center cutting and everything else. This is the only animation I have on this slide. So there's my graphic. The TIR is a little bit off on that tool, but that's all I could throw in there for you. So let's talk about radial relief. We talked about end relief, right? End relief creates the space that we want and for we don't rub when we're plunging and when we're ramping down. So on an end mill, we have radial relief, which is on the outside of the end mill. The end mill cuts on the side, peripheral. So there's three types of relief that you can put on an end mill. All important when you're choosing the right end mill for the right material. They all have their purpose. They all work in certain materials in certain situations. The first one is a cylindrical relief. Now, cylindrical relief is more seen in drills than it is in end mills, but there is cylindrical relief on end mills, mainly in non-ferrous end mills. What that means is you have a margin on the end of the tool that has no relief in it. It's cylindrically ground. It's round, as if you're grinding the whole tool. You're leaving a little bit of that cylindrical ground on there, and then you're doing a primary and a secondary behind that. Mainly run in non-ferrous materials and mainly to stabilize the cutter as it cuts. A sharp cutting edge in non-ferrous material is going to want to grab. It's going to want to chatter. It's going to want to chip. It's going to want to do all that stuff. But by adding a margin on the end of that tool, microscopic, depending on how large it is for different materials, it will stabilize the cutter. It will get that thing to stop chattering depending on what kind of axial length cut you're actually making on there. So that's your cylindrical relief. The next one is eccentric relief. Eccentric relief, in my opinion, is going to give you the biggest bang for your buck. Okay. If you're looking at an end mill, if you're running super alloys, if you're running your pre-hard alloy steels, if you're running your Inconels, if you're running your pH stainlesses, 15.5s, 13.8s, all that stuff, you really want to make sure the end mills that you're using have eccentric relief on them. This is what's going to give you the biggest or the largest amount of strength behind your cutting edge. So the relief on eccentric is more of a rolled off relief. So instead of doing like a flat grind relief where you're just going to put a steep angle on the end of that, we're actually rolling the relief down. So it's more of a gradual relief and it provides a lot more strength behind the cutting edge. So when you have something resharpened at a local grinder, you're probably getting flat grind relief. So just be mindful of that. Make sure that if you can, if you're not going to the OEM to have your tools reconditioned and you're using a local house, they're probably going to take an eccentric relief in maybe 8 out of 10 cases, or maybe 6 out of 10. I won't say 100% because some people do eccentric, but they're going to put a flat grind on it, and that's going to basically change where you're going to run with speeds and feeds. The last one is flat grind or standard relief. This is where you basically create your geometry, use a cup wheel or a flat wheel, do a primary flat grind and a secondary flat grind. This will give you the most clearance. It'll prevent rubbing, but it'll also give you one of the weaker cutting edges too as well. So those are the three reliefs on there. You have a cylindrical relief, you have an eccentric relief, and you have a standard relief. So hopefully that helps explain the geometry a little bit more. We can get in a little bit more detail and probably later dates. We have an hour here, so I'm trying to be mindful. I see my moderator, Jeff, kind of looking at me, making sure that we're on pace. So I don't want to be backed up here too much. So end mill wear patterns. So basically there's 4 types of end mill wear patterns that we're actually going to talk about today. The first one is a wear land, which in my opinion, a wear land is not really a problem. It's kind of an ideal situation. You're trying to create a nice even wear land on your cutting tool. But this is where when you run your tool and you look at it, you're going to see a nice even, no chipping wear land or a shine all the way down the cutting edge. Now, what determines whether or not that tool is performing by that wear land is how large that wear land is and how quick that wear land shows up. But these are the best scenarios to fix if you have a nice even wear land. Because if your tool's not lasting and you have a nice even wear land, what I'm going to do right away is I'm probably going to take a bigger chip and slow down your RPM. Because if it's not lasting and you have a wear land on the end of the tool, which means it's not cutting, You're starting to flatten the end of the tool. Number one, it's a perfect situation because I know your vibration, your work holding, and everything else is ideal. And we're just wearing that tool out. 9 out of 10 times, we're probably wearing it out because our surface footage is too high. Because if it was chipping, which we're going to get to on the next one, my surface footage wouldn't be too high, my feed would be too high. I'd be putting too much force on it. So wear land is ideal. That's what we're looking for. So if you have a nice even wear land, but you're not getting the tool life, I'm going to make a recommendation right now. Increase your feed, leave your speed where it's at, or bring down your RPM. Now, I don't normally recommend as an application engineer slowing down a spindle at all. And you don't always have to slow down your spindle. You don't have to slow down your machine, because if you're getting an even wear land and I see that my RPM is too high for that, what I can do is bring my feed up so I'm actually gaining cycle time. And if I had the opposite where I was seeing chipping, what I can do is bring my RPM up. So I'm not slowing down my feed because I have chipping. That's something very good, and some things I like to point out, especially when I'm working with a customer up front. The last thing we want to do as application engineers, the last thing we want to do as Harvey Performance, when anybody calls us, and the last thing you guys want as customers or anybody that's running a tool and trying to solve a problem, is to slow it down. Nobody wants to slow it down. Sometimes you have to, but there's things we can do with the end mills to increase that productivity and not slow it down. So jumping into the chipping, so a chipping is pretty easily recognized, right? It's nicked or flaked ends on the end of the tool. It's usually caused by a number of things, a number of things. We have one thing on here that we listed because it has to do with the cutting tool. And we said it's being caused by excessive loads in the metal cutting operation or thermal cracking, where we're feeding it too fast. We're putting too much load under that tool. That's what happens if you have the ideal situation of your work holding is good, your spindle's good, you're not running out, you're not hanging out of the holder. There's a million other things. We're trying to stay focused on how to fix the tool if you've identified all the other problems with your situation. But chipping, too much feed. Remember that. If you're chipping, too much feed. If you have a wear land, but you're burning up the tool and it's wearing out too quick and flattening the end, probably too much speed, too much surface foot. So the next one's thermal cracking. So this is a good one to kind of dive into a little bit. So in milling, cracks perpendicular, so they're going to be opposite, perpendicular to the cutting edge, are most common types of thermal cracking. They're going to go perpendicular to that. These cracks propagate slowly and they lead to accelerated wear and chipping. So what causes thermal cracking? Ineffective coolant application, exaggerated temperature fluctuations, excessive feed rates, where we're bringing heat in there. What we're doing is we're bringing heat and then we're throwing coolant on it, then we're cooling it down, we're heating it up, and that causes thermal cracking. So I have not a theory on this, but again, I get all of my information from experience. It's always good to consult people that have experience, okay? I get all of this from experience. A lot of people ask me, do I run coolant? Should I not run coolant? What should I do with this material? How do you suggest that? I'm going to give you my insight on this. If it all depends on the tool path you're running. Tool path is king. With running an end mill, running all these tools, tool path is king. The first thing I'm going to ask you whenever you talk to me about having a problem is, what's your tool path? Because if you're running an HEM or a high efficiency tool path, which is your adaptives, your dynamic milling, your master cams, your eye machining, those types of things, heat does not become a problem as much as it used to in traditional tool paths. So if you're running an HEM tool path, my recommendation, and this is just my experience, I always run coolant. Very rarely will I not run coolant unless my material gets up 58, 60, 65 Rockwell. I will always run coolant. I have 100% always seen better results in my tool life with coolant and high efficiency tool paths. Now, when you run a traditional tool path, you're bringing in a higher radial step over, a lighter axial, but a higher radial step over, and you're inducing a lot of heat. You're putting a lot of heat into that end mill. I don't recommend doing traditional tool paths anymore, but there is times where you actually need to, and there is technology where you need to. This is where you need to start being mindful of the heat that's generated on there and then splashing coolant on it. If you're doing this, I still recommend coolant, but I would make sure that your coolant flow is always on your tools. You're always keeping an optimal temperature and you're not just kind of blasting it and the coolant is actually hitting at the cutting edge. So that's very important when it comes to should I use coolant or should I not use coolant? The last one is fracture, which in this case is catastrophic damage when it comes to a cutting tool, right? We break the tool, we chip the end mill. This again, improper selection of speeds and feeds, obvious. I love, that always being the cause, right? Because we always look at that. Hey, my tool broke. My tool's wearing out. The tool chipped on the end of it. What caused it? Well, you didn't run the right speeds and feeds. Well, okay, there, Captain Obvious. I figured as much. Maybe there's something we need to do with the speeds and feeds and make adjustments. So improper speeds and feeds, consult the right material, the right speeds and feeds for that. Depths of cuts, coating. Coating has a lot to do with it. Do I have the right coating for that material, for that helix angle, for that rake, for that release that we talked about? Loose work holding, these things, pull studs, dirty taper, all these things have to do with that. So the remedies are pretty obvious, right? If we're breaking, the force is going to be huge. So the first thing we want to do is if we're breaking and we've identified that there's no problems with everything else, we want to look at the force of that end mill. Carbide's very resilient. It's tough, right? It's going to want to perform to the best of its ability. So if it's breaking, there's something that's induced in your environment that's causing that tool to break. So we need to dissect that. We need to find out what it is and get it fixed. So there's two basically, this is just wrapping this up. There's two basic problems that we have with tool wear, right? We have thermal stresses, we have mechanical stresses. Your thermal stresses are your workpiece inconsistencies, right? Let's talk about the workpiece. Let's talk about the material we're cutting, right? This is a big thing as an application engineer. We all walk into situations where we need to purchase stainlesses. We need to purchase alloy steels, low carbon, high carbon, super alloys, Inconels, and stuff like that. Do we know what the consistencies are? We buying from a reputable place? Are there hard spots in that material? What's the workpiece consistencies and inconsistencies in there? Work hardening. Work hardening is a big thing. Certain materials, austenitic stainless steels, Inconels, they want to work harden. So if you're not taking the right speeds and feeds, you're going to actually make the next cut a lot harder than the first cut. And usually when an end mill likes to settle in and make that first cut, it just wants to go and it thinks everything's going to be straight and everything's going to be good. So if you start work hardening your material by not taking the right depths of cut, that end mill is not going to survive very long, and that could give you catastrophic failure. When we get into drills, this will be a good thing with drills, work hardening, because how many times have we ever did a lot of tapping in our applications and we go into austenitic stainless steel and the tap keeps breaking and we keep going, man, these taps aren't working. These taps aren't working. They keep breaking. They keep breaking. I'm telling you right now, it's not the tap's fault. The drill is probably not doing its job. And the drill is probably work hardening the hole, and that could be a lot of your problem. So be mindful of the work hardening of certain materials and make sure you're taking the right chip load so that doesn't happen. Heat resistant materials are really huge for work hardening. Rubbing, underfed conditions, those are your thermal stresses. Your mechanical stresses are your tangential cutting forces. That again, your tangential cutting forces can be controlled by that helix angle we talked about. Flute count, core strength. We can control these, control the controllables. We have variations. If you ever look in the Harvey tool catalog, or if you look in the Helical Solutions catalog or Micro 100, you notice we don't just have one end mill. We don't have one helix angle. We don't have one flute count. There's a variety of helix angles, coatings, flute counts, geometries. That's because they all act differently in different situations. We can help you with that. Our application engineers can help you with that. There's a lot of experts out here in the field that can help you with that. Abrasion, chip congestion. Chip congestion, there's a mechanical force. I'm breaking the tools. Well, maybe we have too many flutes. Maybe our radial cut. Maybe we need to back off on a flute and actually get more chip room. Suspect tool holding and work holding, huge one. Unmanageable metal removal rates, MRR, metal removal rates. How much material am I removing? So that means my radial depth of cut, my axial depth of cut. That means my feed that I'm running. That's the combination of your metal removal rates. Is it too aggressive for what I'm trying to do? I have a thing called the MRR triangle that we'll be launching in another video. So the MRR triangle, just to give you a little snippet of this, I'm going to whet your appetites for next time. So the MRR triangle basically are three things that you're controlling to get the best optimal material removal rate, and they're consistent on axial depth, radial depth, and feed per tooth. This triangle, you can do amazing things with it to fix your problem without changing any cycle time or reducing tool life. Very, very good. That'll be coming soon. So let's jump into drill point design and application. Like I said, I'm a old school drill point guy. I started, believe it or not, at a company called, which you might all be familiar with, Precision Twist Drill in 1987. Yes, that's how long I've been actually doing this. And I started working on points and points on all drill, high speed, and then I got into carbide. So very important. The drill point is one of the most important. No, wait a minute. Not one of the most. It is the most important part of a drill, because let's look at a drill in three phases. Real simple, three phases. A drill makes a chip, a drill carries a chip, and a drill gets rid of a chip. That's it. So your drill point is making your chip. The flutes are there to just hold the chip, and then the helix is there to evacuate the chip. It's very important to make sure the right point geometry is there for cutting your material. This consists of a chisel edge angle, which is the center of the tool, a chisel edge, a cutting edge, a rake face angle, and then you have clearance angle on the point geometry. This is where is very critical. So let's dissect into the drill point. The drill point is the working end of the tool. That's what's doing all the work because it's making the chip. The chisel edge is the first point of contact on the drill, the center of that drill. The chisel edge creates the major thrust force. So the force that's being put on that drill, whether it be high-speed steel, whether it be carbide, whether it be powdered metal, whether it be ceramic. I'm not sure if there are ceramic ceramic drills right now, but for some of the Inconels, it's probably not a bad idea. So it's creating all that force. So the chisel edge angle, its accuracy, along with accuracy of the alignment of both of those cutting lips, control the hole's position, size, and straightness. So the correct selection of drill point geometry is paramount to the tool's performance. Because if you add force to the drill from the point, your hole is going to walk, you're going to get bad finish, you're going to break, crack, fracture, and everything else. So it's very important to create the least amount of force with the end of the drill because it controls the drill chip formation. It controls the size and shape of the chips, controls the chip flow through the flute. It controls it. Controls hole size and accuracy, controls size and amount of burrs produced. Burrs, the right point geometry and selection of point geometry is gonna control the burr at the top of the hole and the burr at the bottom of the hole, the exit burr. And this leads to increased secondary operations, deburring, flipping parts, and everything else. So you can get the right point geometry that's gonna reduce that. Increases strength of the cutting lips on the outside of the tool. What's the first thing to go? The outside of the drill. Cracks, fractures. Reduces cutting lip wear, reduces amount of heat generation. Heat is a killer. So let's just take a look at this. High thrust forces, torque and bending motion occurs. A chisel, a chisel edge, the end of the drill, which controls the web. Remember, web on a drill, core on an end mill. The end of that drill, a chisel has 10%, a chisel of 10% of the diameter causes 70% or creates 70% of the thrust. 70% of the thrust. So if we look at this as a standard drill, 10% of that diameter, 70% of the thrust. If we can thin the web, so find a drill, use a drill with a split point geometry on there, you are going to reduce the thrust force on the drill by 40%. 40%. So high speed, a little bit more prevalent, a little bit more common in these cases where you don't have a web thin, but the split point has a lot to do with the thrust force on the end of the drill. It will reduce the thrust force by 40%. Split point drills, very critical, 140-degree split points. Main advantages, reduces thrust force, but that's not the only thing. It manages the chip formation. It gives you a couple more cutting edges. So it's going to break up that chip, make it a little bit smaller, help evacuate it through the flutes, improve centering ability. So what it's going to do is it's going to help self-center. High speed, it's going to walk a little bit more. Carbide doesn't walk as much. So if you're even using high speed or cobalt drills, you're going to want to find a drill with a split point, and you might not need to spot the hole. When I use carbide drills, I hardly ever recommend spotting in some cases. There are advantages to spotting. But if it has the right geometry, the right split point, it will self-center itself. And you can get faster penetration rates too as well. So now maybe instead of running 2% of the diameter on a feed, we can run 4% of the diameter. Or instead of 2 thou per rev, we can run 4 thou per rev, just because of that split point geometry that's actually on there. So let's take a look at the coolant benefits of, and then we're getting close to wrapping up here. But let's take a look at the cooling benefits, right? The cooling are bringing coolant into a situation where you're using an end mill or a drill actually serves three purposes, not just one. We're not just cooling. The whole word coolant sounds like coolant. We're cooling the heat zone. That's it. But number one, and first and foremost, running the right coolant system, whether it be a flood system or a through coolant, really helps and assists in evacuating the chips. Very critical. One of the main killers in end mills is recutting chips. That's a huge thing. We do not want to recut chips. And if we don't want to recut chips, we either got to use an air blast or we got to get that coolant to move the chips out. That's number one. Number two is it provides lubricity at the cutting edge. The coolant not only is going to cool, but it's going to add lubricity. It's going to make the chip slide down the flutes easier. We're trying to add the right coatings to the materials to take the porosity out of the cutting edge, to give the slickest surface, to make sure the chips don't adhere to the cutting edge. Very important in your titaniums, very important in your aluminums. We need the coolant to add lubricity. And then number three, offers heat dissipation, right? We want to reduce the heat as much as possible. Taking the right strategy, the right tool path is going to help do these things, but adding the coolant is going to benefit. Remember before when I talked about, should I run coolant? Should I not run coolant? See, these are the things and the advantages with me personally, where I've run tests for hours with coolant and without. These, I think, are some of the benefits you actually get by bringing in coolant. Is you're not only just cooling the surface, you're evacuating the chips and not allowing it to recut chips. You're adding that lubricity and you're bringing heat dissipation. Now, there are reasons to not run coolant. Don't get me wrong. I'm not saying that there's not situations not to run coolant. Coolant sometimes is an added cost. I think it's a savings, but sometimes it can be an added cost and it can make machines a little bit dirtier and dingier when it comes to that. So very important. So let's take a look at a good, better, best scenario. So if you look at these three situations on coolant benefits, you got a good situation, which is like an MQL system where you're just kind of putting coolant on intermittently. So you're not really getting the benefit of the coolant flush, but you're getting the lubricity and you're getting a little bit of cooling effect. The better situation is where you're running a flood coolant, where you got your lines coming around, you're actually flushing the chips. Even if you're drilling where this scenario is showing, you're getting the coolant all the way down to the point of the drill. You're going to get that a lot better with a coolant flood than you will with like an MQL system, because it's really going to get you when you're pecking, or it's just going to add that lubricity to the outside of the tool as it comes out of the hole. And then your best situation, even on end mills, is a coolant through situation. Whether the coolant through is actually coming out of the flutes, out the OD, or whether it's coming out the end of the tool. This is going to give you, especially in a drill, all the coolant concentration right at where? Right at the point of the drill. What the most important part of the drill is the point. We want to get the coolant down there. We want to make the chip down at the bottom. We want to curl it. And then the coolant that comes out the end of the drill is going to flush those chips up the flute with the right coating and give you ultimate tool life, ultimate productivity. So let's kind of just close up here with tool holding and run out, because I think this is very important to kind of close out everything we talked about before. Because if you don't have the right tooling and you don't have the right holder and you don't have the right run out of your spindle, then all that time you put into getting the right geometries on your end mill, getting the right geometries on your drill, all that effort you made and consulting is going to be wasted in a poor tool holding situation. So we need to use the right holder, whether that holder be a hydraulic holder, whether it be a shrink fit holder, whether it be a high precision collet holder, whether the projection is correct on that. We want to make sure we grab the right holder. Keep your holders clean and in good shape. Good shape. Very important to make sure that the holders look in good shape. Now, we talked about coolant, right? One thing I wanted to bring up with holders in good shape and coolant is make sure you have the right concentricity on your coolant and it's maintained. Because if you run a lower concentricity on your coolant, you can see these holders start to rust, oxidize, and you're going to have problems. So important to maintain the right levels of concentricity in your coolant. And yes, concentricity in coolant will change depending on what material you're actually cutting. So keep that in mind too as well. Don't maximize your ER collets. I've seen this a lot of times. What does this mean? Very simple. Don't use a 1/4 inch end mill and use a 9/32 collet. Okay. Will it work? Yes. Will it ruin your collet? Probably. Will the TIR be sacrificed? Absolutely. Try not to maximize your collets. Now, I told you I've been doing this for 32 years. I'd be lying to you if I told you I never did it myself, but I also had to pay the consequences of poor tool life and the rest of it. So it's very important not to maximize your collets. Use the right collet for the right holder. Check for cracked collet nuts. That's a big one. We can crack collet nuts, especially if you hit the fixture. If you just touch it, you generate heat into that collet nut, it will crack too as well. And your pull studs are very important. So if you look at the influence of concentricity on tool life down here, if you take a tool that's running out 50% of the feed, your tool life will be reduced by 65 to 85%. That's a rough number. It's not, I can't pinpoint it, but I'm telling you, that means if your feeding per tooth is 2.5 thou per tooth and you're running out 1 thou, 2/10, you can sacrifice your tool life by 65 to 85%. It's very critical to make sure that run out is good. You're using the right tool. You didn't grind the shank and stick it back in the holder. For every 1/10 of TIR run out that you're actually having, you're looking at roughly about 10% of tool life lost. 10% of tool life. So it's important to make sure that all that is checked. It will also decrease your part finish. Not only does run out decrease your tool life, if you're looking to get a certain RMS or an RA on your end of your part, depending on what that is, TIR can directly sacrifice the part finish that's on there, because each tooth is going to cut unevenly. One tooth is going to take a little bit more of the load. And when you get into micro tools like Harvey tool and you start getting down at your 10, 15, 20 thou diameter end mill, boy, think about how that TIR really affects how your run out is. So it's very critical. Usual suspects: spindle taper condition, drawbar backlash, tool holder, wrong pull stud, previous crash. Nobody's ever crashed a machine, right? I said that on a presentation before. I've never broke a drill, an M mill, and never crashed a machine. And if you believe that, then yeah, COVID-19 is not going on, I guess, right? But no, that's how we learn. We crash these things, but make sure that the machine's in good shape. Short tool shank grip. This is another one. If you're trying to go over toe clamps or obstructions, make sure you have a minimum of 2 times that diameter in the shank. That's a minimum. Like to see 4 times, 2 times the diameter up in the shank. That would be great. We've all pulled them out. We've held on to that. That will create TIR and all kinds of run out issues. So make sure you're not using shorter lengths of cut to actually run your parts. And with that, guys, our every folks that are on this call, I appreciate your time. I know Harvey Performance appreciates your time. I know that these things in these times, it's kind of hard to be away from our normal everyday things. So hopefully we as a company can provide a little insight, a little help, even if you take one thing away from this and you walk away and go, I'm going to take a look at some helix angles. I'm having some pull-out issues. Maybe I need to go with a slower spiral on my end mill. If you take that away from this, we've done our job, and we're happy that you guys joined.